Hello and welcome to Video Podcast 3.3. In our previous vodcast, we overviewed the water cycle, and the focus of this vodcast is running water. Shown on the screen is the water cycle image that we considered in the previous vodcast, and in that vodcast we talked about evaporation, precipitation, runoff, infiltration, and transpiration, among other things. But our focus from this point forward in Chapter 3 is going to be runoff. The central focus for this chapter is understanding how water reshapes landscapes. I'm going to start off this runoff discussion by taking a broad lens view of the movement of water across land. Drainage basins are land areas that contribute water to a river system. The bottom left image shows you the Mississippi River drainage basin, and it is enormous. As depicted in the top right image, just about any water between the Rocky Mountains and the Appalachian Mountains is ultimately going to funnel its way to the Mississippi River. The middle picture shows the Kankakee River drainage basin, and I included that because that's the river that I grew up on. The Kankakee River runs through Will County, gotta represent my 815, and it extends all the way into northern Indiana. Now the river is shown as that little blue squiggly line, but the yellow shaded region shows you the drainage basin for the Kankakee River. Basically, any water that enters that yellow region will ultimately make its way to the Kankakee River, and any other creeks, streams, or rivers will eventually dump their water into the Kankakee River, assuming they're part of the shaded yellow region. Any creeks, streams, and rivers outside of that yellow shaded region, in the orangish colored region, will not contribute water to the Kankakee River. It's also important to note that drainage basins are separated from one another by divides. A divide is an imaginary line, but it's a line that sits at a high point, and any water that falls on the left side of the divide will flow down to the left, and any water that falls on the right side of the divide will flow down to the right. This image shows three primary drainage basins, and the highlighted drainage basin, the one in the center, shows a river that originates in a high elevation region and eventually dumps into a large body of water, say the ocean or a gulf. So let's take a look at the typical river profile. A river system will carry all of the water that flows into it from its drainage basin. The headwaters are where a river starts. As an example, the Mississippi River's headwaters occur somewhere in Minnesota, and the mouth of the river is where the river ultimately ends. The mouth of major rivers most often occurs at large bodies of water like oceans and gulfs. For the typical river profile, there are three distinct zones. The first zone we're going to talk about is what's called the sediment production zone. This zone occurs towards the headwaters. This river zone typically has the steepest gradient, which means the water tends to flow pretty steeply downhill compared to other regions of the river. What's important to note about the sediment production zone is that through weathering and mass wasting, there will be a lot of erosion occurring in this region. The steepness of valleys and the fast flow of water is an excellent combination for producing sediment and transporting sediment. That's why we say that the sediment production zone is an erosion dominant zone. Sediment will be carried from one place to another. The image to the far right highlights a portion of the sediment production zone for a river, and the brown, muddy appearance of the water is excellent evidence that a great deal of erosion is occurring in this region. The brown color is due to suspended sediment in the water. The next zone we're going to consider is what's known as the sediment transport zone. Notice that the river starts to get a little bit more curvy in this region, and we call that curviness meandering. The gradient in this region is nowhere near as steep as it was in the sediment production zone, but the side-to-side swiveling of the river helps keep the water flowing and the sediment moving downstream. The final zone that we're going to consider is the sediment deposition zone. In this region, the gradient gets really flat, and that causes the river to slow down significantly. As the river velocity decreases, a lot of that sediment that was being carried through the river in the sediment production zone and the sediment transport zone will start to settle to the bottom of the river because the stream velocity isn't fast enough to keep it from falling to the bottom of the river. Through deposition, the sediment will start to accumulate on the bottom of the river, and ultimately, you can see the formation of a delta. For the Mississippi River, the mouth of the river and the delta are located in Louisiana. The last thing I'll talk about in this vodcast are the factors affecting flow velocity. The velocity of a river will vary along a stream and throughout time. Flow velocity depends on a few different things. First, channel slope or gradient. The channel slope tends to be highest at the headwaters, and then the slope decreases rapidly as you start to approach the mouth of the river. Flow velocity also depends on channel size and cross-sectional shape. The channel size for a river will increase as you move from the headwaters towards the mouth. Another factor affecting flow velocity is channel roughness. Channel roughness and channel slope are strongly correlated, as you can see by taking a look at the graph shown. The channel will be roughest towards the headwaters, which is why you often see whitewater rapids in those regions, but the channel will smooth out significantly as you move from the headwaters towards the mouth of the river. The last factor we'll consider that affects flow velocity is the amount of water flowing in the channel. Discharge is defined as the volume of water that flows past a certain point during a given time. And as the image shows, the discharge will increase as you move from the headwaters to the mouth. Okay, that concludes this video podcast. Our next considerations will be stream erosion and stream deposition.